Hello everyone, my name is Marcelo Milani, and I'll be talking about one of the main results of my PhD thesis, and that's an elementary bound for the directed grid theorem. I'll also be introducing a mathematical object which was used in order to obtain such an elementary bound, and that's what we call a cycle of well-linked sets. This is joint work with Meike Hatzel, Stephan Kreutzer, and Irene Muzi. So before I can tell you about what exactly our results are, I want to give you some introduction about the context in which our results happen, and they all start with the parameter of directed tree width. So what is directed tree width? This parameter was introduced around 2001 and 1999, and it works in a way which is somewhat similar to undirected tree width, in the sense that we have a directed tree, and the nodes of the tree are what we call bags, and these bags, they are subset of the vertex set of our digraph D. Okay, and now when we take all the bags together, they have to give us back the set of vertices, and we also want all bags to be disjoint, but we also allow the bags to be empty. So it's almost like a partition, but we allow empty parts. So this is somewhat, but it's a little bit different from undirected tree width, and another difference is that on the edges of our tree, we have a set of guards. So these guards are again a set of vertices. And the point of this guard is that whenever we look at some subtree of our tree, for example, this red one, if you have some path that leaves the subtree and goes back to the subtree, then this path must intersect one of the guards. And so in a sense, what this directed tree width is doing is trying to understand or try to express how complicated the strongly connected components of our digraph are. And so the width of the tree with the composition as can manage is going to be the maximum of the union of the bag and the guards. So if you take an edge, the union of the bags and the guards. And so if you need to make like the bags or the guards very large, it means our strong components are somehow very complicated. So why is this parameter interesting? It has a couple of applications, both in terms of algorithms and in terms of graph theory. And for algorithms, one thing that one can imagine, since we have a 3D composition, if our width is small, one can apply dynamic programming techniques to show that the disjoint paths problem can be solved more efficiently if the directed tree width is small enough. So this is a result from the same people who introduced directed tree width, from Johnson, Robertson, Seymour, and Thomas. And so similar to undirected tree width, we can ask ourselves, okay, we can do dynamic programming if the directed tree width is small. What happens if the directed tree width is large? Do we gain anything? Do we learn anything from our digraph? And so the question that they ask us, what's the structure of digraphs with high directed tree width? And they also propose a conjecture which would tell us about what the structure could be. And the conjecture is the following. So they conjecture that there is some function f such that every digraph of sufficiently high directed tree width contains the cylindrical grid, or for the k, as a butterfly minor. So what is the cylindrical grid? We can see an example here of the cylindrical grid. We have several concentric cycles, directed cycles, all directed the same way. And we have several paths which intersect the cycles, and these paths are always alternating. This one is leaving, this one is entering. And so this is the cylindrical grid. And a butterfly minor, that's a concept of minors for digraphs, which is somewhat similar to undirected minors, but we have some additional restrictions. So we are also allowed to delete vertices and edges, but the contraction operation is somewhat different. We say that we can contract an arc UV if it's the only outgoing arc of U, or if it's the only incoming arc of V. So that's a butterfly contraction. So this arc in both cases we can contract. And so we can say that the conjecture is that they can obtain the cylindrical grid by edge deletion, vertex deletion, and butterfly contractions. So this was a conjecture, and it was proven a couple of years later by Kobayashi and Kreutzer, and they gave a non-elementary upper bound for the function f that we have here above. So by non-elementary, I'm saying that this function f that we obtain is a power tower of 2's with some polynomial of k on top. However, the height of the power tower is again some function of k. So it's a very large power tower, and this is what we call a non-elementary function. So because the height is not a constant, it's non-elementary. If you have here this being a constant, that'll be an elementary function, and that's the main result of our paper. But before I present you our main result, I would like to tell a little bit about how these non-elementary functions pop up in the literature. So toward this end, I want to consider some of the arguments used by these two papers, which I would say they've somehow formed the base of the directed theory of directed minors. So one way that these non-elementary functions they can pop up is by using recursive arguments, something like induction, for example. So when using induction, you might be in some situation where you have, for example, the vertex set of a digraph, and you want to find, let's say, for example, directed cycles, as in this paper. So in your argument, you might say, I can find some directed cycle here. However, to do this, I'm going to lose some vertices of my digraph in order to make the cycle. But we can only apply this if the subset we're looking at has some special properties. So it could be that by deleting this cycle, I lose actually a lot of vertices here. And so the next valid set, which I can continue, will be only this small set, which now has to be large enough so that I can apply my function recursively with k-1. So we can do this one to get the first cycle, and so in order to get k cycles, we will need to get here to be large enough. So we can apply f of k-1. And so this whole thing that we lose, let's say it's called g of k. The g of f of k. And because you have like the whole set, and so this has to be like the size of the whole set. And so if you have something like this, our f of k would be, so the digraph has to be large enough so that we can apply f of k-1. However, we have to be able to afford to lose a certain number of vertices. And so we can end up having something like this, like f of k is g of f of k minus 1. And the issue where we get things to be non-elementary is precisely on this function g, because often in this sort of argument, we want to use something that we call iterative Renzi. So we apply Renzi's theorem. However, in each step of our recursion, we apply this Renzi theorem once. Another technique that we often also like to use in this kind of result is to use the pigeonhole principle on the power set of vertices, to say that we get some set of vertices that behave in some specific way. And so, for example, if we need this set to come from Renzi, so for example, to have like some large clique for us to be able to apply our arguments, then we end up in a situation where this function g is not a polynomial function, and so this explodes into a power tower whose height depends on k. Right, and so this means that if you want to get an elementary function in the end, we can only afford a constant number of applications of Renzi or the pigeonhole principle over some power set. And so what this means is that in order to go from a non-elementary function to an elementary one, this is not just about optimizing some constructions, optimizing some constants. We really cannot apply a whole set of proof techniques which would otherwise be very useful in obtaining the result. So we really need to come up with new techniques in order to break through this non-elementary barrier. And the reason why we do this is that by applying more restricted techniques, we are possibly getting closer to what's actually happening on our digraph, so we're also gaining new insights into the structure of digraphs. So let's go to our main results. So what do we obtain? So the first result that we get as a step to get the cyclical grid is that we get what one can call a cyclic grid. So what is the cyclic grid of order k? So it is similar to the undirected grid, but the columns, they are oriented from top to bottom, and the rows from left to right. So here we have k columns and k rows. And what we get is that the end of this cyclic grid is well linked to the beginning. So let's say this set is A, this set is B, and we're going to say that A is well linked to B, and this means that whenever we take some set A prime here and some set B prime here, it can be any set of vertices, then we find some linkage connecting A prime to B prime. So I said adjacent paths. These paths, they can intersect this cyclic grid, but they do not intersect each other. Okay, so to obtain such a cyclic grid, we require that the true width is again a power tower. However, the height of this power tower is just the number 8. So it's a constant and not a function of k. So this means this is an elementary function. So the previous results that I mentioned, the one about the grid theorem, for example, they also obtained this cyclic grid. However, what they get is a non-elementary function for this. And so by applying previous results, we can already get some improvement over what's already known, and we get the following corollary from the theorem above. And that we can get now, again, some power tower of height 8, such that every digraph satisfies one of the following. Either D has k vertex decision cycles, or we can find some set X, such that by deleting X from D, we obtain an acyclic digraph, and the set X is not very large. And not very large, I mean it's some function of k. So Reed, Robertson, Seymour, and Thomas, they proved something similar. So this is what we call people call Younger's conjecture. However, the function that they gave here, as before, is non-elementary. So in our way to get an elementary bound for the directed grid theorem, we also get an elementary bound for Younger's conjecture. And to the best of my knowledge, this is the first improvement of the bound for this conjecture. So the third result that we get, and the final one, is that we can now get some function f3, now power tower of height 22, such that if the digraph has true width large enough, then it contains the cyclical grid as a butterfly manner. So we got an elementary bound for the directed grid theorem, which, just recall, Garlet and Kreutzer, they gave a non-elementary upper bound for this theorem. So now I would like to tell a little bit about how our proof is structured. So first, of course, we start with a high directed true width, and from the digraph of high directed true width, we show that it contains what we call a well-linked ordered web. So what is such a web? It consists of two linkages, P and Q. Q is sorted from left to right, that's why it's called ordered, and P is intersecting Q on this order. However, Q can intersect P on any order, and so it's only ordered in one sense. So for this, for example, would be an ordered web. And just like with the grid before, we have that the end of this web is well linked back to the beginning. So this is well linked. This step is also present on the proof of Karabayashi and Kreutzer. However, there they use this iterated Renzi argument, and in order to obtain an elementary bound, we managed to replace this iterated Renzi argument by some application of the Lovesh local lemma. So this allows us to bring this step down to an elementary function, and that's kind of like the starting step towards the grid theorem. So after we get this ordered web, we construct what we call a path of well-linked sets. This is inspired on the work of Shekori and Chusoi, in particular on the path of set system framework that they introduce in order to obtain a polynomial bound for the undirected grid theorem. And the path of well-linked sets looks like this. So the definition is somewhat similar to the one for the undirected case. However, the mathematical properties, they are very different because directed connectivity behaves very differently. So we have a bunch of sets, which we call clusters. So let's call it an S1, S2, and S3. And each cluster has the property that the left side, let's call it A, and the B, right side, let's call it B, that A is well linked to B. So this is well linked. Right, so for every cluster we have that it's inside well linked from left to right. And on the outside, we have this linkage that simply connects one set to the next in a path-like fashion. Right, so that's why it's called a path of well-linked sets. We have here the sets organized in a path-like fashion, and inside it's well-linked. And just like before, we have the property that the end of the path of well-linked sets is well-linked back to the beginning. And so already from this path of our linked sets, we can obtain our first result, which is that we can construct from this a cyclic grid where the end is well linked to the beginning. Right, and then by applying this result from Reed and others, we can get a better bound for Young's conjecture from this step. So towards getting the cylindrical grid, we need to get to the cyclic grid. But to get the cylindrical grid, we need to somehow close the cycles in a way that they become disjoint. So here, remember, I say the end is well linked to the beginning, but the linkage that we get connecting this, it may cross everything in the middle. So a large part of the proof consists of getting this back linkage to be disjoint. And when we do so, we obtain what we call a cycle of well-linked sets, which, as you can imagine, it's similar to the path of well-linked sets, but the clusters, they are organized in a cycle-like fashion. So they are also well-linked from one side to the next. And we get the linkages connecting here. And then for the last step, the hard part is to get this final linkage to be disjoint from the rest. And so in order to obtain this with the elementary bound, we have to use a framework that we introduced earlier. And that's a framework which is based on temporal digraphs. And the temporal digraphs, they kind of allow us to analyze how the paths in this ordered web behave. So if you remember, for the ordered web, we have this connection from left to right. So this kind of gives us this notion of time. And so we use these temporal digraphs in order to analyze how the path P intersects this linkage Q, and then we can use this to construct the well-linked clusters individually. So this is a rough overview of how the proof works. So I'd just like to, again, summarize our results. So from the cycle of well-linked sets, we get the central grid, which gives us the grid theorem. And so overall, we obtain 4 mathematical objects now with elementary functions. So all 4 of them previously had only non-elementary bounds for how we can obtain them. And now we get elementary bounds with power towers of height 5, 7, 8, and 22. So all of these objects, they somehow play an important role in the digraph structure theory. The ordered web is often used both by Reed and others to get the disjoint cycles for Young's conjecture, and in our proof and the proof of Garlet and Kreutzer to get a cylindrical grid. And so one natural question that arises is that we get now elementary functions, but what about polynomials? Can we get this down to a polynomial? And currently, the only lower bounds that I'm aware of, they come from the undirected case, and so they don't tell us much about the direct case of these objects, and they are all polynomial lower bounds. So maybe for some of them, we can find a pseudo-polynomial lower bound for the central grid. That's not so clear, but it would be nice if you can get at least tighter lower bounds that tell us that the directed case is somehow different from the undirected one. That would already be very interesting. So thank you very much for watching, and I hope you enjoyed the presentation.